Today we're going to be making a start on chapter 3, which is about forced oscillation, and we're going to be looking at some standard signals, some non-periodic signals, and some sinusoids. So first off, I'll talk about the approach that we're going to take in terms of solving these problems. Okay, and then we'll look at some non-periodic excitation, so that involves step forcing functions, some ramp forcing functions, and some decaying exponentials. We'll then look at some periodic excitation, so in particular we're going to be looking at sinusoid. We'll talk a bit more about non-sinusoidal periodics next week when we talk about Fourier analysis, but here we're going to be looking at periodic excitation, that's the sinusoid. Then we'll be talking about what happens in real life with a damped response, and then a specific case called beating, okay, which we're going to look at. So what's the approach that we're going to take? Well, basically, we have a single degree of freedom undamped system. So this has obviously got damping in, but an undamped system will obviously would not have the C in, but you've got basically a differential equation, okay, where this is obviously the second derivative with respect to time. And we have a forcing function at the end, f of t, okay? F of t is the forcing function. And we've got this differential equation, and basically the math behind it is the same as you would use in mathematics when you've been given a differential equation and said find the solution. Well, we're doing exactly that, but obviously this is in the context of a vibration problem. So with an undamped system, obviously this is with a damped system with a damping. Let's first look at an undamped system where we've got where C is 0. The solution to this equation will follow this format, okay, where xcf, cf is what's known as the complementary function, and xpi, pi is stands for particular integral. And so it's made up of these two values added together. Now what's xcf? xcf is the solution to this function with no force, okay? So last week we covered, well the week before last, we covered undamped free response and damped free response. And so what you do for an undamped system is you take that undamped free response, and that is your xcf, okay? The free response is what xcf is. xpi, though, is what takes into account of the force, okay? And we'll go through how to solve this problem in quite a lot more detail, because xcf we know the solution to, okay? And so your complete response will be a component that's the free response plus the component that's due to the force, essentially, okay? And what happens is in a real damped system, xcf will slowly decay away to nothing, okay? And you'll be left with just the pi bit, because obviously xcf, as you know, a free response that's got damping. As you start the oscillation, it will oscillate, and then the oscillation will die out to nothing, okay? Whereas xpi will be left with you, okay? Because obviously that's the bit that's due to the force that's being applied, okay? But obviously in an undamped system, then xcf will remain with you as well. xcf is a complementary function, and xpi is a particular integral. Okay, and like I say, complementary function is the free response, and pi is due to the forcing function that's being applied. So in the case of an undamped system, the solution looks like this. Okay, we've seen this before, undamped. Okay, so you've got an amplitude times by cosine, and the cosine is with a frequency of omega naught, which is the natural frequency of the system. Okay, and you can also write that in terms of A1 and A2, which we covered last week, okay? The fact that these two things are equivalent. And you saw that in the tutorial as well. Okay, and then so obviously omega naught is root k upon m. A1 is A cosine phi, and here we've got A2 being minus A sine phi. In the case of a damped system, you've got this as your free response, okay? The only difference being this is now alpha, not phi, and you've got this decaying exponential in there as well, e to the power of minus zeta omega naught, and your frequency is now omega d. There should be a t there. Apologies. It's amazing how many times you go through a set of notes before the year starts, and you continue to spot problems. So this is on page. So on the top of page 36, okay, there should be a T after the omega d in that equation, okay. Apologies about that. So yeah, for a damped system, the solution looks like this, okay. And again, you can separate the A cosine blah 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 into a cosine and a sine term. And again, omega naught is root k upon m. Omega d is now a function of zeta and omega naught, and then a1 and a2 are the same things in terms of alpha now instead of phi. So XCF is easy. Okay, you've done it all before. If you know you've got a damped system, then you've got this solution. If you've got an undamped system, then it's this solution. Okay, straightforward. Right, XPI. Now XPI, to find XPI, the particular integral is basically it's quite a crude method of trial and error. What you do is you look at the force, okay, that's being applied. That'll be a certain function, and your particular integral is going to be of the same form of that forcing function. Okay, and so I've got a little table here, and the table's in your notes. Basically, if your force is a constant term, then you make a trial solution, okay, that's a constant term, and you solve for what the unknown is. And here, constant term, I've called it C here, and what I do is I try a trial solution, and I've called it, and these Greek terms down here are all the things that we're going to try and work out. Okay, if it's a constant term, then I'm going to try a constant as my trial function, and we go through and solve it. You'll see that in a second. If it's a polynomial, so some function of time, okay, and that function can be written as a polynomial, then you try a polynomial of the same order. Okay, so if this is a t squared term, then obviously r is going to be t. Okay, but the alpha and the beta and the gamma and so on, you'll have to solve yourself. If it's a sinusoid, then we try a function of a sinusoid, and that's one form of a sinusoid. Okay, that's very similar to the free oscillation solution, but obviously if it's a sinusoid, then we try a sinusoid as our solution. And lastly, if it's an exponential, then we make our trial function to be an exponential. And the reason I'm calling it a trial function is we test it out. Is this a solution? And if it is, what are these values of alpha and beta and gamma and all that sort of stuff? Okay, so we're going to go through and solve those things. So it's a trial function, and like I said, the choice of trial function will depend on what your forcing function is. Okay, so if your forcing function is a polynomial, then this is what we try. And if your forcing function is an exponential, then we try this one, okay? And so on and so forth. And basically we find these values, okay, based upon our differential equation, and then you can then solve for the whole problem. And you get a general solution, and then you apply initial conditions to get the exact solution. So let's have a go. Here we've got a rectangular step forcing function. So at time less than 0, we've got 0 force, and then suddenly at time 0, we have a force of F0 being applied constantly. Okay, so it's a step forcing function. What is the response to for a single degree of freedom undamped case? So here, after t equals 0, the equation of motion looks like this. Okay, so it's undamped. There's no c term. We've got mx double dot plus kx equals F0, where F0 is a constant. Okay. And so we know that our complementary function is the free response to an undamped system, which looks like this. Okay, that's the alternative form where it's in terms of cosine and sine. Well, A1 and A2 are just arbitrary constants. We'll find them out in due course, depending on our initial conditions. But at the moment, let's leave them as A1 and A2. We'll find them out soon. Now, the particular integral, we try the trial function of a constant, okay? Now, in that table, I call that constant gamma. It can be whatever I want, okay? Bananas, whatever. But I want to find the value for that constant. And so what I do is I take my XPI, I take the first derivative with respect to time, and that happens to be 0 in this case. I take the second derivative with respect to time, and obviously the derivative of 0 is 0 still. So XPI double dot is 0. And what I do is I take my value for the XPI and XPI double dot, and I stick it back into my equation, my differential equation. Okay. So where I had mx double dot down here, obviously I stick in my double dot term, that's 0, and I take in my xpi term and I put that where it was kx equals f naught. Okay, so I've still got my force down here, and it's quite clear that if you solve for gamma, you end up getting f naught upon k. That is my particular integral. Okay, so what you do is you take your particular integral, you take the first derivative and the second derivative, and you stick it back into your equation of motion, your differential equation of motion. And by sticking that into the equation of motion, you'll find the unknowns. Okay, here we've got gamma comes out to be f naught upon k. And so we've got our complementary function, we now have our particular integral, you can therefore get the general solution. So the general solution is the complementary function plus the particular integral, and so there's my complementary function, the free response, plus my particular integral at the end. Now this is called the general solution, and it's general because it doesn't matter what your initial conditions are because you've got these arbitrary constants in. Okay, depending on your initial conditions, you can therefore find A1 and A2, but it will always be in this form. Now what I'm going to do, that's the general solution. What I'm going to do is I'm going to apply some initial conditions, and the initial conditions I'm going to apply is that at time equals 0, the displacement is 0 and the velocity is 0. Okay, at x of 0 will be 0 and x dot of 0 will be 0. So the displacement and velocity are 0. And those initial conditions are called initial rest conditions because obviously the thing isn't moving. And then suddenly you have this force being applied. What is the response? Okay. So there's my initial conditions. X of 0 and x dot of 0 will be 0. And what we have to do, therefore, to find that is we take our equation for x, this one here, okay, and we have to differentiate with respect to time once to get velocity, and then we apply our initial conditions. So that's differentiated first with respect to time. Obviously the cosine turns into minus sine and the omega naught comes out, which is why that's there, and there's a minus sign. And then obviously the sine turns into cosine and we have an omega naught that also comes out. Okay. So we take 0 for time and we plug it in. So we plug it into the equation on the previous slide where time is 0 and we end up getting A1 plus f naught upon k equals 0. Therefore A1 must be minus f naught upon k. Yeah, do we all agree? Take the previous equation, this one down here. Okay, if you stick in t as 0, obviously cosine of 0 is 1 and sine of 0 is 0. And so you stick in 0 here and 0 here, you get 1 here and 0 here. So therefore you end up with A1 plus f naught upon k must be 0, which is down here. Okay, therefore A1 must be minus f naught upon k. And then if you do it with this equation, you stick in t in here, sine of 0 is 0, so that term disappears, cosine of 0 is 1. Okay, so you end up with A2 omega naught equals 0. There is no way that omega naught can be 0. Okay, otherwise that would be 0 frequency. A2 must therefore be 0. Okay. And so we can plug them back into the equation. So we take our value for A1 and A2, we put them back in here. A2 is 0, so that term disappears. And we have out front here minus f naught upon k. And if you rearrange it, you end up getting this equation. So that's the solution to a rectangular step forcing function under initial rest conditions. Okay. Here's the solution, okay, and then you apply, you can plot it and it looks like this. Okay, so you start off at time equals 0, there's no force, so it's not moving. You apply that constant force and the thing will start oscillating, okay? You apply that step forcing function and obviously it's being applied and so it's going to oscillate backwards and forwards because we've got an undamped system, it will continue oscillating backwards and forwards and it'll oscillate around this position here, f naught upon k, okay? Notice that's your static forcing, static displacement, okay? And obviously it's oscillating between 0 and 2 times that, okay, backwards and forwards. What about a linearly increasing forcing function? Okay, so here our forcing function, instead of just being a constant, is some constant multiplied by t. Okay. What do we try as our trial function? Well, let's look at that. Complementary function as before. Okay, it's an undamped system, so we just use the standard form that we found before. But a forcing function, okay, that's linearly increasing, is actually a polynomial of t, but the order of that polynomial is 1. Okay, so we end up with an equation that looks like this, alpha t plus beta. Don't forget that t to the power of 0 term, okay, because that won't necessarily always be 0. Okay, don't forget so when you've got like t squared plus something times t, okay, if that's your forcing function, don't forget the t to the 0 term, the term without a t in it. Okay, you must always remember that term, which is why on that table, if we go back to the table, there we go. Here's my degree r term. If r is 1, you've still got this c term that you need to consider. Okay, over there, gamma in this case. Obviously, I've only got 2 terms in the previous one, so I called it beta. It doesn't really matter. Okay, so we try that as our forcing function. As our particular integral. It's based upon our forcing function. And so we go through. We differentiate with respect to time. You take the derivative with respect to time here, you get x dot pi is alpha. And obviously, you take the derivative of that again to get the second derivative. And obviously, the derivative of the constant alpha is 0, so that disappears. And you plug that back into your equation of motion with the forcing function. So x double dot is 0, so you have m times 0 plus k times alpha t plus beta equals ft. Well, what you can do to find alpha and beta is you can group the terms together. So anything that's got a t in, you can set that equal to ft. And anything that's got t to the 0 in, you can set it equal, in this case, to 0. Okay? So it's quite clear to see that alpha is f upon k and beta is 0. Okay, if you can prove that if you set alpha to be f upon k in there, you get k times f upon k. The k's will cancel, you end up with ft equals ft. Okay, that makes sense. So that's grouping the t to the 1 terms. We can see that alpha is f naught upon k and beta must be 0. So you can plug that back in, okay? xpi is fk upon t, okay? Yep, and which means you end up with ft upon k. Okay, so we basically take our alpha and beta and we plug that back into that term, okay? f upon k is alpha and beta is 0, so you end up with ft upon k being your particular integral. We then add that to our general solution. So there's our complementary function. Again, the standard form plus ft upon k. General solution. What's a1 and a2? Well, let's work them out. Differentiate with respect to time and stick in t equals 0. So there's the solution. Here's the velocity. If we set t to be 0 in this case, we end up with a1, 0, and and 0. Obviously, if t is 0, then that term is 0. So we end up with a1 must be 0. Okay. If this is 0 and time is 0, a1 equals 0 because these 2 terms here are both 0. But down here, if we take time as 0 for this case, we end up with a1 omega naught 0, so that disappears. a1 was 0 as well, so that obviously that's doubly disappearing. a2 omega naught times by 1 plus f upon k. So you can find out what a2 is. Applying initial conditions, a1 was 0, a2 is minus f upon k times omega naught. And so you can stick that into our general solution and you end up with this as your solution. So there's our a2. a1 was 0, so that gets rid of the cosine term. Here we end up with a sine term multiplied by some amplitude and then plus a ramp function. Okay, a thing that's going to increase as time goes up. Okay. Now I haven't plotted that, but you can see quite clearly what happens. This bit on its own, okay, it's just a ramp function. Some constant times by time, so it's going to increase as a line, straight line, where the intercept is 0. But obviously here we've got an oscillation. So what you end up with is an oscillation that's increasing, that's not increasing in amplitude. The amplitude remains the same, but the total force or the total displacement is going to be increasing. Okay. So like I said, I haven't plotted it here, but you can quite see that. What about if we've got a decaying exponential? And so we have our forcing function, which is some constant times by e to the minus something times by time. Okay, so it's decaying, and we've got a value here tau. Okay, which is tau is the constant in front of time. Okay. If tau is big, then it takes ages, and if tau is small, then it's going to be quick. The trial solution, the forcing function was an exponential, while trial solution is the exponential. And notice that the constant in front of t remains the same. I don't change that. That's still minus 1 upon tau. Okay, but alpha I don't know. I've got to work it out. So I take the first derivative with respect to time. Okay, obviously what happens is you get a minus 1 upon tau coming out. So I end up with minus alpha upon tau out the front. And I take the second derivative, where again I take another minus 1 upon tau out, and I end up with plus alpha upon tau squared. I stick that into my differential equation. Okay, so the x double dot this time is not 0, it's this term. So I stick that in here, I've got this term over here. What is alpha? Okay, well what we can do is we can cancel out the exponential terms, they disappear, we don't need to worry because they're in every term. We end up with this as our term. And obviously if you solve for alpha, you end up with f naught divided by m upon tau squared plus k. Okay, that's quite clear. If you take alpha out of both of these terms, okay, alpha's out front, you end up with that term in brackets. You then divide both sides by that term, you end up with alpha being that relatively complex fraction of fractions. So our particular integral is we take our alpha term, we plug it back into what we had as our trial function, you end up with this. And so if our general solution will look like that, okay, so there again is our complementary function, which is the free oscillation, and then you have your alpha term times by the exponential. Let's apply initial conditions again. Initial rest conditions, so there's our general solution, there's the first derivative. Stick in t equals 0, what happens for this case? Obviously that a1 times by 1, okay? a2 times by 0, so that term disappears. Over here, what happens if t is 0? What's e to the 0? 1, okay? So we're left with this term plus a1. And so a1 must therefore be minus that term. Now for the velocity, okay, so we've got this term out here. What happens when you take the derivative of this? Well, another minus 1 upon tau comes out, multiplies that by that thing. Obviously that makes that tau squared drop to tau down here, but obviously you multiply by k by tau, and that plus turns into a minus. This term, obviously you get the minus sign, you have cosine, turns into minus sign, omega naught comes out. Sine turns into cosine, and you have an omega naught coming out. T equals 0, this term goes to 0, this term goes to 1, so we end up with a2 times by omega naught, and obviously this term drops to that, because the e to the 0 is 0, sorry, is 1. And so we've now, in this case, we've actually got a value for a1 and a2. Okay, they're both functions of this term, okay, this is a minus that term, and here we've got plus that term, but we've also got an extra bit in the denominator down here, omega naught times by tau. And so you can apply that out here. So we have that term out here, and then we've got sine omega naught t with that with this bit down here. Okay, so there's our a2 sine omega naught t, and then a1 we worked out was this, just that term. So we just end up with cosine omega naught t, and then we've still got that bit of the particular integral down there. So that's the solution. You can see it's a sinusoid, okay, because you've got a sine and a cosine. You've got an decaying exponential, okay, and that sinusoid multiplied by the decaying exponential has got a certain amplitude, which depends upon what t is. Sorry, tau is. The other way you can write that equation is knowing that omega naught is root k upon m, you can actually plug it in and you get a slightly different solution down here, okay? So you end up with this bit changing. Now what's interesting about this, if you remember, for for the if you remember, for the rectangular step forcing function, we had x equaling f naught upon k 1 minus cosine of omega naught t. Okay, and that was for a rectangular step forcing function where you've got basically that. Now here we've got a decaying exponential, which normally would look like that. Okay, but if t is huge, you end up with something that looks a bit like that, or even that. And what happens if t is huge? If that term is big, that term disappears. If that term is big, that term disappears, and you end up with, and if that term is big there, you end up with 1 here. Okay, you end up with 1 minus cosine omega naught t, which is this. Okay, so if tau is big, you end up with that function, which is what we had back in, when we were just looking at the step forcing function. If tau is big, that term disappears because 1 over a massive number is 0. Here we've got 1 over a massive number, which is 0. And here we've got e to the very, very small number, which is 1. E to the 0 is 1. And so you can you end up with the rectangular step forcing function. So let's come on to this. So for large tau, the solution gets closer and closer to that for a step function, which makes sense. Okay, if your decaying exponential takes forever to decay, you're going to be pretty much close to a step, and you end up with the same equation, which is what we found before. The last non-periodic signal is what's called blast loading. Okay, so like an explosion or something. And here, that shape of that function is basically two forcing functions added together. And those forcing functions happen to be two exponentials. Okay, so if we, I didn't actually write that here, did I? If you look on page 42, you've got this, you've got those two forcing functions. Okay, you've got the two functions that are added together to make that blasting function. And you can see quite clearly on page 42, those are both exponentials. Okay, one's a decaying exponential, okay, and one's a minus decaying exponential. So they both come up, one comes up from below and then levels off. They've got different values for tau, and what you can do is basically you take your solution for the decaying exponential and you solve for both of them. Okay, so it's the same solution for both, except for tau 1 you've got tau 1, one you've got tau 2, and one you've got a minus sign out the front. Okay, there's just a minus sign there. And you add them together to get the solution. The total solution is going to be the solution for x1 and the solution for x2 added together. And so you add them up together. Okay, that's the solution. So that's the solutions for periodic signals when you've got initial rest conditions. If you have non-rest conditions at initial, if the thing is not at rest with your initial conditions, okay, when t is 0, then obviously you have to apply those particular initial conditions when you're going through the solution. So if we're going through, well, there's an example. Obviously, if these terms aren't 0, okay, if x of 0 is not 0 and x dot is not 0 is not 0, then obviously your general solution will be the same, but your exact solution, which is what we worked out down here, that one there, won't be the same thing, okay? Now on your formula sheet, I've given you, if you look at the back of your book, on the penultimate page, so page 3 of the formula sheet, you can see what I've done is for single degree of freedom, the following equation. So undamped, obviously, if you look down, you can see I've given you the general solution for the undamped case, and I've also given you the initial rest conditions, okay, for the undamped case. For the damped options, I've not given you the initial conditions, okay? I've not given you the equation where there's 0 initial conditions, okay? But you can work them out. You just apply the initial conditions and find out what A1 and A2 are. So that's on your equation sheet. Right, what about a sinusoidal excitation? So here's our forcing function. At time is less than 0, we have 0 force, and then suddenly at time 0, we have a sinusoid as our forcing function of amplitude f0 and frequency of omega, which is the omega of my choosing, okay, the frequency of the oscillation. So there's my equation of motion, my differential equation of motion, mx double dot plus kx equals f0 sine omega t, okay, which is that function there. At time is greater than 0. So what I do is again, it's going to be the addition of xpi plus xcf, xcf being the undamped free oscillation equation, okay, which is there. And then we try our trial solution, which is a sinusoid. Okay, so if you look at the table, whenever you've got a sinusoid, you've got this as your trial function, a mix of cosine and sine at that frequency omega, which I'm giving the system. Okay, so that's the frequency is fixed. Okay, if I apply something of 5t, then omega here will be 5 in my trial function. What I've got to find is alpha and beta. And the other condition here is where omega doesn't equal omega naught. Okay, because in that case, when omega equals omega naught, your trial function is actually slightly different. Okay, and in the notes I go through that special case, but it's not in the presentation because it's not, it's not vital for you to know. But if you look at page 46, you can see that it's basically this function multiplied by t, and that's what you've got to do when you have omega equaling omega naught. But we're not dealing with that. Omega doesn't equal omega naught in this case, and so that is my trial function. And if I take the derivative of that trial function with respect to time twice, what happens is you end up with the same thing multiplied by a minus omega squared. Okay, because you take the derivative of this, you get minus sine, and omega coming out, here you get cosine. Take the derivative again, that minus sine turns into minus cosine. Okay, minus cosine, and then obviously what was the cosine with the first derivative comes out to be, goes back to being sine. Cool. So finding the second derivative, you end up getting that, and then obviously you can substitute it into your equation of motion. So when we had x double dot, we've got minus, and then obviously this term, plus k times by x equals f naught sine omega t. Okay? And what you can do is you can see quite clearly that this term and this term are the same. So you take that out, and then you divide by what's left. So we have a k minus m omega naught squared, m omega squared. So that drops down here, and you end up with alpha cosine omega t plus beta cosine, beta sine omega t equaling the forcing function times by sine omega t divided by this k minus m omega squared. And what you do to solve for this equation, what's alpha and beta? Well, basically, you group the sine terms together and the cosine terms together. Okay, so obviously this applies, because you've got a sine omega t and a sine omega t. It's quite clear to see what beta is, yeah? Sine omega t drops out, sine omega t drops out, and you end up with this term. Alpha cosine omega t, well, there's no cosine term over here. So this lot must be 0. The only way for this to be 0 is for alpha to be 0. So it's quite clear that beta is f naught divided by k minus m omega squared, and alpha is 0. So the general solution gives us this, okay? So remember our xpi was alpha sine omega t plus beta cosine beta sine omega t. So obviously beta had a term and alpha has 0. So that's our xpi, there's our general solution. We then apply initial rest conditions. So we take the first derivative, okay? So all the terms are remaining because they're sinusoids. And we solve for initial rest conditions, okay? So when time is 0, x is 0, displacement is 0, so that's a1, that stays here, that's 0, and that's 0. So a1 must be, therefore, 0, okay? With the first derivative, this term drops to 0, that's disappearing. We've got a2 omega naught times by, and that's 1, okay? And then we have f naught omega k minus m omega squared times by 1. And so it's quite clear that we can work out what an A2 is. A1 was 0, A2 is minus omega upon omega naught F naught divided by K M omega squared. And so you can plug it in and you end up with this as your initial rest conditions. Okay. So you have a sinusoid. Depending on your value of omega here and your omega naught here, you've got two sinusoids basically equal, added together. They're subtracted here, but it doesn't really matter. Okay, so depending on your frequency, you're going to end up with a single sinusoid, or a mix of sinusoids. Okay, they're going to be on top of each other. One might be a small ripple, the other one might be a big one. It depends on your values of omega and omega naught. And like I said, this is only valid for when omega doesn't equal omega naught. Okay, if that is the case, then you have to use the special cases in your notes. Okay, the two frequencies were equivalent. It's clear to see that x would tend to infinity. Okay, which obviously doesn't make sense because you'd end up with 0 down here. If omega equals omega naught, you'd end up with 0 down here because we know that omega naught is root k upon m. Okay, well, if you stick in that in here, you end up with this becoming 0. What about if you offset it? So you have a function that looks like this. So at time equals 0, we've got 0 force, and then suddenly you offset it by a certain forcing function, and then you also have a sinusoid, which is a possibility. Well, what you do is you end up with mixing the two equations, like we look with the two decaying exponentials. Well, here you've got basically a constant forcing function and a sinusoid. And so you take the solution for the constant forcing function, that's part of it. You then add on the solution for the sinusoid. And so there's our bit for the constant forcing function, and there's our bit for the sinusoid. Okay, so you just add them together and you get your solution.